Okay, we're going to get started. So welcome, everyone. Those sitting here, those watching us in TikTok now and Zoom. It's really my pleasure to introduce today Professor Joao Marques-Silva. So these days we talk, you hear the three musketeers in AI, the pioneers of deep learning being called the godfathers of deep learning. So Joao is the godfather of deep thinking and SAT solving, okay? And for the last few years, he has been working on logic-based explainability. So he's going to talk about that. He did a PhD 90s in the US, University of Michigan. And since then, he has been in different places in Europe. He has been in University College in Dublin, so you correct me if I say something wrong. So Southampton in England. He has been leading a group on a related topic, okay, so Explainability in Toulouse. And for the last couple of years, okay, he has been in Catalonia, Spain, the University of Lleida, and this institution, ICREA. And the work that has been doing in the last few years is basically in the application of these efficient SAT-based methods, okay, to make AI, in particular deep learning, more transparent. Okay, so there's been a lot of work done on the area. So what characterizes the work that Joao has been leading is trying to make this particularly vigorous. And we're going to talk about that today. Okay, Joao.
Thank you very much. Thank you very much for hosting me, for the introduction as well. And the talk is about what I've been doing for the last few years, based explainability in AI. So, of course, everyone in the room is aware of the successes of machine learning, now these days with LLMs. So this is an example I tried a few years ago. So Explainable couldn't give me an example, and it does perfect job. So it's fantastic in that sense. Of course, I'm not a very good user of LLMs, but still I did this, and I was able to use it for programming. So I asked for an example in Pandas, for those of you familiar with Python, to do something. Again, this was matching some values. So it's not very difficult, but fairly technical. And it did well, I think it is working because I used the code at the time. And of course, you are also aware of the many more successes of AI and machine learning. So robotics, self-driving cars, image and speech recognition, and of course, the successes of DeepMind, and then more recently, all the LLMs, right? So I tried to cover most of them. I probably forgot lots of them, but still, I tried to show here the most important ones. Now, these are the successes. And then there are troubling issues with machine learning in general and LLMs in particular. So this is an example I tried back in 24. How many pairs of twins do you need in a room for there to be at least 50% chance that two people have the same birthday? And of course, everybody immediately knows the answer. But the LLM went down and gave me the completely wrong answer, right? And of course, I decided to check recently. So is it more clever now? It's kind of more clever. So I repeated the question now a few days ago. And well, it avoided to give the answer by saying you don't want surprises, right? So, or that you should have a surprise. So I don't think it's a good answer, but still, just to say that there are changes to the systems being built. If this seems to suggest these systems are getting better, this one became viral a few days ago. So I need to get my car washed. This is in English. Some people saw it in different languages. I have to take it to the automatic car wash, which is 15 minutes away from my house, just a few steps away. Do you think it's worth driving, right? So it's obvious the answer. It's simple. So you should walk. Essentially, the conclusion is you should walk, which of course for us, it doesn't make any sense. So these systems really are not yet there in terms of reasoning. So how do people get trust? So one way is is Explainable AI. It has been around for a few years. You have this very complex AI system, and you have a user. You want to help the user understand what is being done. So this is the simplest definition is you want to help humans understand what these machine learning models are doing. Of course, this raises lots of questions. So how should you do this explainability? So one way is to answer why the prediction questions. Another way is to answer why not some other prediction questions. But of course, this then raises other questions, which is rigor, for example. So should we use what many people have tried, which I call sub-symbolic, non-symbolic methods? Should we use logic-based or symbolic methods? And so the talk will essentially say, well, we should use symbolic methods, but let me go and explain why. So XAI is very, very important. So it started back, the effort started back in 2016. These are slides from 2017, but it started in 2016. GDPR, the European AI Act, so a lot of interest in Europe and worries in Europe about trusting AI systems. I used to have here the American case, and now I don't. I have the Chinese case for obvious reasons, so I'm not going to elaborate on that. And so this is in general, what I'm concerned about is high risk and safety critical uses. So in Europe, people propose this pyramid of risk. So you have situations where the use of AI is not you don't care about. Then you have high risk uses where you can use AI under some serious constraints, and then an acceptable risk where you cannot use AI. And so high risk examples are there. So you have law enforcement, management and operation of critical infrastructure, and so on. Safety critical are, concrete examples are self-driving cars, which I showed a few slides back. Okay, so in these settings, this is so important that some authors a few years ago proposed don't use neural networks, don't use, well, at the time there were no LLMs, but don't use these systems and just use interpretable models instead. Okay, I don't buy that, but I'll talk about this later. In all these cases, correctness of explanations is paramount. You want to build trust. You want people to trust the explanations, to feel that they are not being fooled, right? And you want to be able to debug and diagnose these AI systems. And so this is what we have been doing since 2019, okay? So with some levels of success. So let me talk about that. So this essentially is the talk. So I'm going to start with some basic concepts and then talk about why non-symbolic methods are problematic. And I'll start with the first attempt. Then I will introduce logic-based / symbolic XAI. So how do we do explainability in a rigorous way? And then talk more about more issues with non-symbolic methods. And then go back again to symbolic XAI, something we have been doing recently, and conclude. Okay, so so that we are all on the same page, we really don't. So I'm going to give a lot of examples with very simple machine learning models, but I don't want you to get the impression that, yeah, you cannot do more than that. So we can do much more than that. So of course, for people to understand what is going on, you need some models that are easy to understand. So we will use decision trees, which again, I presume everyone has seen. So the notation might look weird, but it's just because set membership is easier than to use equals, at least for me. And so you can ask questions like, so obviously if x1 is 1, you will predict 1, and the other features are not important. So if you want to change the prediction to something other than 1, which features are important? So these are the type of questions we have been asking for a few years. You can say it's trivial. I'm going to show it's not that trivial. We also, again, another example of a simple machine learning model. Some people call it interpretable R decision lists. Very simple example. For those of you that are quicker, you can quickly see what would be the prediction in this case. And you can build up complexity. It's an example of a random forest. So you have a bunch of forests, each one votes, and then there are different ways to pick which should be the prediction. Usually we assume it's majority voting. You could also use weighted voting. So another quite used example. And of course, neural networks. So for what I'm going to talk about, the activation unit is ReLU, but technically you could use anything you want. And of course, you have many more machine learning models. So for those of you that think the world is neural networks, not quite. There are lots of things to. For example, there was a very nice recent paper on symbolic XAI for k-nearest neighbors by a different group. So, but yes, so people are looking at different machine learning models. And of course, the levels of complexity continue to grow. So this is the architecture of a very simple transformer. And this was a few years ago. So these days, let me see if I have that for you here. Yes, I do. So this is what I got recently, the complexity in terms of the number of parameters of these LLMs. And as you can see, it's up there in the trillion these days. So it's a huge number of parameters. For those of you that have thought about automated reasoning, you look at these numbers and you get very scared. So it's very difficult to do this, but just to say that these are the type of systems that people are using for different purposes. Okay? Questions? No? Okay, so in terms of what is a machine, so I'm going to talk about very simple models, and I'm going to hand wave some results of more complex models. But so for us, usually we talk about classification problems where you have features, a number of features. Each one has a domain. We are not picky about the domain, so it does not have to be Boolean. It can be integer value, real value, and so on. And this allows us to define feature space as the conclusion product. You have a bunch of classes, right? And then the machine learning model just computes a function. We usually ask it not be constant to be interesting, which maps feature space to classes. And what we want to explain is an instance, a point, and a class in feature space. Okay? So the class is the prediction that you get, and we want to compute expressions in this case. Notice that this is abstract, but it could be a loan. You ask for a loan, and you'd like to know why your loan was rejected. Okay? So that is an example that we are interested in. Even though I'm going to focus on this very simplistic framework, we have then extended it to regression problems as well. So that is not a limitation at all. Okay? Very good. So how have people targeted XAI in the past? So there are lots of more ways. Again, these are the simplistic methods that a lot of people are familiar with. So I'm totally sure everybody in the room, I guess, have heard about SHAP. No? Yes. Okay, some heads. Okay, so lots of people have used SHAP or a variant of SHAP. Before that, there was LINE 1 year before, and a lot of people in neural networks have talked about saliency maps, which I categorize in the same class, feature attribution. Then you have feature selection. So essentially, the idea is that you pick a rule that explains, so if this holds, then the prediction or the value of the model is going to be that one. A well-known example is anchors. The references are up there. Okay. And then some authors have proposed intrinsic interpretability. So you forget about everything and you just use a model which is interpretable. Okay. This and I already showed you a paper from 2019 where this was proposed. Okay? Yes? Questions until now? Criticisms in the end. Okay, very good. So how do these things work? Anchors, essentially, this is the output of anchors. So it writes this nice rule saying if all these conditions hold, then this is the body of the rule, then the prediction is going to be this one. Again, some people, a good number of people use anchors to get rules. SHAP is extremely famous and it uses assigns relative importance to the feature. So it assigns weights. You can do that globally or locally. I will focus on the local explanation. So you look at this and immediately say, oh, age is the most important for this prediction. Okay, it becomes apparent when you look at it. Okay, yes? Okay, so this is an example of feature selection. This is an example of feature attribution. Very good. Okay, so they are model agnostic. So this means they don't care, they don't know the details of the model. They use sample to understand more or less how the model behaves, and they offer no guarantees of rigor, at least into my definition of rigor. Okay, very good. So let me start by some misconceptions that people usually have regarding non-symbolic ways of doing XAI. So let's start with intrinsic interpretability. So the idea is that you deploy an interpretable model. Okay. So what is an interpretable model? Decision list, decision tree, decision set. Everybody agrees that they are interpretable, of course. And of course, there are a few other models. And the explanation is obvious because the model itself is the explanation. Okay? So, of course, some people have argued that interpretability is fairly subjective because different people see things different ways. So let me ask you a concrete example. This is a decision tree. Again, I will keep the example simple, of course. What is the explanation if for 0001 with prediction 1? So if the model is interpretable, the tree gives the explanation. Okay, so in this case, it should be, well, whenever x1 is 0, x2 is 0, x3 is 0, and x4 is 1, I predict 1. Right? It's obvious, right? So this is what you can conclude. And so you could say that this is the explanation. So these 4 literals are just the numbers because the value of the literals is implicit by the instance is the explanation for this prediction. Right? Can you do better than this? Anyone? Well, some people cannot answer because they know the answer. So the answer is, well, actually, it's pretty clear that you can, right? So if here, instead of doing this path, you flip here or you flip here, you don't change the prediction. So why bother, right? And so essentially, an explanation would be, well, if not x1 and x4, you are for certain, given this model, you predict 1. Now, this is much more intuitive than this here. Now, the funny part is that you can make this as painful as you want. So imagine that between x2 and x3, I now create y1, y2, y3, y200, y1000, all branching to 1. So the explanation provided by the decision tree would be fairly cumbersome, and you can make it much simpler. Okay, so this example is concocted. You could say, come on, that's a concocted example. Of course, again, this one cannot make it simple, but we'll talk about that later. So let me, if you don't believe me, and you don't have to, of course, this is an example from a paper in 23, and the authors were going from a curve model, so that's a way to induce decision trees, to a simpler model, more intuitive model. And the question I asked was, okay, fine, let me find the explanations now. So let me try to see if what the tree is giving is as simple as I can make it. So, the features have these values, and so what you have to do, it takes a little bit of time. I can assure you that you are going to end up here and here. Okay, if I still remember. And so the question is, what should be the explanation? So for the left branch, if the model is interpretable, well, you just do it's F5 less than 99, F6 less than 100, and so on until you get here. So you have 4 literals in the explanation. Okay. So if I should have it here, yes, would be the explanation. Now, if you analyze the model, actually, you can see that 2 literals is enough. Okay, which is again for a human, it's easier to understand. Now, this was what Card would do. The guys in 23 proposed that model. And now this one is even more funny because if you follow the path, it's 1, 2, 3, 4. So you have 1, 2, 3, 4 literals. Now, if you do logic based, you get 1 literal. So as long as F8 is greater than or equal to 94, you predict no matter what. That's what the model says. It's not me. So this means just using the interpretable models is not the solution, right? So if you're not convinced, I have more examples. So here, let me, okay, yes, male, no, 2 minus, male, no, 2 minus, we are here. So you should grant the loan. Again, a paper from 21. I think it's immediate for everyone that some of the literals are going to be irrelevant, right? So if you do the 3-path explanation, that's what you get, which is sophisticated, let's say. And if you do it logic-based, it's much simpler. Again, I could go on. And again, what we did is that we analyzed hundreds of papers, and it's all over the place, even books. Even the book using the AI course here at Hacken, the restaurant example, the tree has this type of redundancies. We checked. So you could say, come on, that's everyone can do that by hand, so why bother? Well, so this is a paper from NeurIPS 2019. It's an optional decision tree. You cannot do better than this. And so the instance is 0010, so 00101. So 00101. So you are here. And the prediction is 1. Okay. So the question is, what should be the explanation? So one way would be, well, you do the path, which is what the dogma of interpretability gives you. So this would be what you get. Okay. Now we analyzed and we said, well, actually, all these littles 1, 2, and 4 are irrelevant for the prediction, and so you can create this much simpler explanation. And notice that here you do a little bit of analysis, so it's not immediately intuitive why it should be the explanation. Okay, so just doing topological analysis of the network is not of the tree is not enough. Okay, yes, can I continue? So this essentially the bottom line is, yeah, interpretability is a myth. Continuing, so another work people have done is model agnostic explainability. So the idea is as follows: you have a black box model, you have an explainer that samples from some distribution, or for example, given training data, you sample the model, and from this you construct an explanation. Okay, so there are lots of examples that do this. In feature attribution, both Live and Sharp do this, and in feature selection, Anchors does this. Okay, so all the most popular methods do a variant of what I'm just showing on the slide. Okay, and so the question we ask is actually we asked several questions, but for now is, can we trust the rules that Anchors is producing? So if it's a rule, it should be a rule, right? So we asked that question, and I'm going to give you some numbers. So this is from 2019. So these are the percentage for some data sets, the percentage of incorrect rules. So 3 is actually good, and this is really bad number. So most of the rules are not rules. Okay, so the bottom line is that they were not rules at all. That's what we concluded back in 2019. Actually, self-criticism, what we did is we compared against an induced model. So we compared our explanations in the induced model compared with what Anchors was doing, but Anchors is ignoring the model. So it can be criticized.
What do you mean exactly when it's ignoring the model?
So it just samples, but it does not encode logically encode the model.
So this is not accommodating other scenarios, just the particular input.
Just check. No, you can, in case of Anchors and Line and Sharp, it uses the input distribution, and then it samples even that input distribution. It samples the model, and from that it goes and creates this rule. Okay. So here people can criticize what we did because we ignore the model. Sorry, we paid attention to the model, but Anchors is ignoring the model. So what we did afterwards is this. So we decided to ask the question, okay, what properties should these systems have? Okay. So we proved back in 2019 that succeeds. So let me go back to this. Sorry, this. So this I just focused on this one. Actually, you can also have redundant explanation. Okay. So this means it's not succinct. So let me go to the next slide. So we proved back in 2019 that if you look at the model, pay attention to the model, it's not succinct, and you can have counterexamples given the model, which can be criticized. And what we did more recently is we asked different questions. So we asked that the three, we have been asking this question for a few years, but we don't have an answer. For these two we have. So we should, the rule that you compute should be consistent with the instance. So if you are explaining bank loan rejection because of your age, the explanation should not be inconsistent with your age. Right? And actually proves that it can, let me quickly, so we prove that these two also fail. So it can be consistent with the instance, and actually can even be consistent with the sample that you start from. The rule that you create can be inconsistent with the sample. And finally, subjectiveness, meaning you should not have two instances with different prediction with the same rule. We have not found an example. So maybe this will never be found, but we thought it might happen. So let me show you some data. So these are the percentage of P1 issues and P3 issues that we found, and it's a pretty significant number. So this means that Anchor is going to give you explanations that are either inconsistent with the instance or inconsistent with the data set you started from, which is extremely troublesome. Okay? Okay, very good. Yes, can I continue? Okay, so let me quickly introduce what we mean by explainable AI. So Well, I start with the,
Why do you say that this is a misconception about non-symbolic AIs? In some sense, you're talking about criteria you have to add on top.
well, yes, it is criteria, but notice that if it's not consistent with your data, what rule?
What is the non-symbolic part of it in the way? It's the fact that you're just
It's
looking at the input.
yes, you ignore completely the model. So you suppose you have a random forest to make it. So you have a random forest, you know the search space, and you are sampling a little bit, and then you are making a conclusion given what you sample. It can be complicated. Okay. And by the way, usually the sampling is not so it's a variant. It starts from training data, but it's not training data. Okay. So I'm going to introduce the definitions. First definition of symbolic explanations. Again, a decision tree that. This is the model, the framework I propose: domains, feature space, classes, and then the classification function. And so an objective explanation answers the question why the prediction, and it constructs a rule. If the logic holds, then the prediction is going to be this one. So, for example, in this case, if not x1 and not x2 and x4, so I'm going to predict 1 because this is what I'm trying to explain. Okay. So this is one type of explanation we are interested in. The other type of explanation is contrastive explanation, which is why not some other prediction. So for example, if I want to change to 0, you guys agree with me that if I change everything else and I just change x4, I change the prediction. Okay. So I want to say this is what I need. Everything else I fix. If I change this guy, I change the prediction. Yes. And so, of course, to keep, we like simple notation, so we just use the sets because everything else is implicit. So in this case, the explanation is 1 to 4. In this case, it's just 4 because everything else I'm fixing. Okay. So this is, of course, intuitive still. So let me formalize this. So given an instance, a weak updated explanation answers a question for all points in feature space. So notice again, I need to look at all points in feature space, all points. If I fix the guys in X, then I guarantee that the prediction is what I am. It's a logic rule. Okay? And the contrastive explanation thinks the other way around. So I'm given a set of features. Every feature not in Y I fix, the features in Y I let them take any value that I want, and I want to be able to change the prediction. So, for example, my bank loan was rejected. What do I need to change to get it approved? Okay, so this is the type of questions I'm interested in. So, actually, for those of you familiar with the topic, this is very much related with adversarial examples in machine learning. So, I want to be able to change the prediction, and I want not to change too many things. So, here I'm not formalizing, not changing many things, but that's why I say it's a weak. Because then I'm going to talk about subset minimal. So, by the way, in terms of reasoning, for those of you interested in, of course, usually reasoning with the universal quantifier is going to be tough. So, what I do is I negate, and essentially these two formulations are very similar. So, here I want to satisfy, here I want to falsify. I want to prove I cannot satisfy. Okay. So, to find subset minimal, you can use it this way. Actually, there are much simpler ways. This is just to say you want a weak XP, and then the proper subset is not a weak XP, a weak XP, and a weak XP in this case. Okay, so it's easy to formulate. Now, of course, where are the details? So another point which is quite important for those of you familiar with the work of Reiter, each XP is a minimal set of the set of CXPs and vice versa. So we prove that, which is quite helpful when you want to navigate the space of explanations. Now. So there's a few questions. So where is the logic? I mean, well, of course, besides the logic formulation, you need to encode the model and neural networks and reinforce and so on. Okay. So this is where the logic comes along. Okay. And of course, how do you decide consistency or not consistency? You use SAT, SMT, mixed integer linear programming, and so on. So this is where it comes along. Okay. Questions? And of course, for those of you that have. So, as I said already, there are strong connections with the adversarial algorithms, and in recent years we have exploited that, and I'm going to mention this very shortly. Can I continue? Yes? Okay, so just an example. So, using the definition, so for example, 1 to 4 is a weak XP, and I show that the definition holds. 1 to 4 is also a weak XP, and I show that the definition holds, and in this case it's subset minimal. And 4, as I said, few slides today is a rich XP, and I showed that the definition holds. Okay, again, a lot of hand waving, but I think it's for those of you with the background, it's easy to see that this is, of course, correct because I already showed the examples. Yes? Okay, so notice that some things, the AXPs in this case are 1, 4, 3, 4, and by doing minimal linking sets, I get 4 and 1, 3. Again, this is what Reiter back in 87 proved. Well, not in this case, but in a related topic. Okay, and of course, we use this extensively when we are computing explanations. Okay, another example, and again, here I'm just going to say that what I did is I introduced another note here just to say that you can have arbitrary redundancy, which I just emphasize this myth of interpretability that people use when they talk about explainability. Okay, very good. So what else? What was the progress until a few years ago? This is what we did. So we showed that lots of classifiers computing one explanation was in polynomial time. So the naive-Bayes classifiers, decision trees, lots of graphs, monotonic classifiers, propositional languages, all of this we could compute in polynomial time. So those are the best news possible. We have fairly good news. So we show that for random forests and decision lists and boosted trees, it was computationally hard, but effective in practice. So we found logic encodings which work very well in practice. And so we can place them here. Computationally hard, we solve them very quickly in practice. And then at the time, this was until 2022, we could really not analyze, well, we never tried to analyze Bayesian networks, we tried to analyze neural networks, and we could just do a few tens of neurons. Okay? So this was what we got. More recently, two different groups, ours and others, show that actually for neural networks, changing a little bit the paradigm, you can reason about fairly complex neural networks. Okay? So, so this, of course, the field itself is much more than just computing one explanation. It's just the number of topics that we and many others have looked at in recent years. And of course, I stopped in 24, not because the research stopped, but doing this drawing was difficult. So many more topics since then, because other groups have joined in, and now there are lots of more topics being studied. Okay, so just to say that it's not just computing some explanations. Okay, so from the beginning, people would say, come on, guys, you cannot do neural networks. What are you talking about? And that was always very distressing, because it's not true. So let me show you very quickly that logic really is fantastic, if you guys are not already convinced. So this is a very simple model. So you have input layer, output layer, hidden layer. And besides the first, all the layers you compute an intermediate value from the input using the matrix of weights and the bias vector. And then you compute the output by using the sum activation function, in this case, ReLU. Okay, for those of you that have seen this before. Okay. And so what I just said very quickly was this. So you start by computing an intermediate value, which is the dot product of the matrix A by the input, then you add some bias value, and then you take the max, which is the ReLU operation. Now this is very easy to encode. Okay? So the idea is that each of those entries is just a summation, right? A sum of products, and then you add some component, right? And then how do you ensure that you represent how the neural network works, the ReLU activation unit? So you do the difference between two non-negative entities, yi and si, and you ensure that only one of them can be non-positive at each time. And you do this with an integer value variable. That's it. The encoding is not ours, it's from other guys in 2018, and we just used it. Okay, so it's very easy to do. So the punchline is that certainly the logic encodings are not a limitation in terms of representation, are not a limitation for XR. There are limitations in terms of reasoning, of course, but in terms of representation, it's really easy to work with. Okay, now, so what could we do 2 years ago? It's already 2026. So this was results we presented in 2024. And in 2019, as I said, we could do around 20, 30. Sometimes we were likely to do 40 neurons. In 2024, this went up to almost 100,000 neurons, which is pretty good. By the way, this requires changing the definition to being distance restricted. So we are looking around the point we are trying to explain. So this is fantastic, but of course, the speed at which I started the talk by saying a trillion parameters, here we can do 100,000 neurons. There is a gap here, which we don't know yet how to fix. Something we have done more recently, not just us, but others as well, is a logic-based model agnostic XAI. Okay? So we start by the definition of collective and contrastive explanations, and we just replace feature space by sample space. So please pay attention to the slide. Did you see the change? That's it. So we change from feature space to the sample space. So what is sample space? Well, give me training data, you have a sample space. If you trust training data to train your model, why not trust training data to explain your model? And this is quite nice because you can compute all CXPs in polynomial time. We prove this. We can compute an expression polynomial time. Some others will improve the complexity. And we can do fairly efficient enumeration of objective explanations. And of course, you still have minimal eating set while doing, as I said, to the work of writer. And guarantees of rigor, well, the machine learning models are induced from samples. So if you trust the data, you should trust explanations that you get. So yes, this is a limitation. So if you trust the data, you can then compute these explanations. And we have been working in this field, in this space recently. Okay, so let's go to one of the other problems. So, Shapley values are extremely famous. Everybody, I presume, have heard about Shapley values. So they were proposed for game theory in the 50s. They have been applied actually in AI for more than 20 years. So there is a paper back in 2001 that mentioned the use of Shapley values trying to explain models. They were more formalized in 2010-14 to measure feature importance. And they became hugely popular with Sharp in 2017, so almost 1 decade ago, okay? And you use this to, as I said at the beginning of the talk, to assign importance to features, okay? So actually, it's really important. This one is fairly old, I presume it's still there. So you go to Shapley value Wikipedia, and it has a section on machine learning. So it's that important, okay? It's there. Yes? Very good. So, so the question we asked is, do Shapley values really provide a rigorous measure of feature importance? It's a fair question. So it's used for feature importance. Is it rigorous or not? So let me talk about that. So what we did was the following. And again, notice that I'm not talking about the tool, the Sharp tool. I'm talking about the theory the Sharp tool uses. Okay. And so we analyze the Sharp scores in theory. We ignore the tool. We just look at the definition of Sharp scores. So I have two very similar decision trees, decision tree 1 and decision tree 2, right? So here you have the predictions that they make. As you can see, there is a small difference, minor difference apparently, which is what you predict here and there at the bottom. Everything else is the same. Yes? Very good. And we are going to try to explain this instance here, 1, 1, 2, 1, which both of, sorry, 1, 1, 2, which both of them predict 1. Yes? So we can start by asking questions like, okay, give me the AXPs and CXPs. And it's intuitive that if you want to fix the prediction to 1, you fix 1. You don't care about the other ones, the other features. Right? So if you change 3 or 2, as long as X1 is 1, you are guaranteed to predict 1. Right? It's always here and there, yes? Both of them. Okay. And if you want to change the prediction, there is no other way. You need to change 1. You don't care about the other ones. As long as you change 1, you change the prediction. Yes? So this is really, okay, so if you don't trust me at the adversarial examples. You ask what are the minimal adversarial examples, and you get 1 as well. So there's no other way. You need to change 1, otherwise you cannot change the prediction. Yes? Okay, so let me go back to how do you compute Sharp scores in theory? You start with an instance, as we are doing in XAI, and then you look at the points where, given some set, you fix the features in that set, and you care about the points where those features take that value that you are interested in, the value that comes from the instance you are trying to explain. Okay? And so the characteristic function that is used is the expected value of the model when you take points from the set that you define. Yes? So this is what was proposed in 2010, 14, and 17. This is what is used. You use the expected value of the model for when you specify some set to fix the features. And then, as soon as you have this is the definition of Shapley value. So you have this weighting component. You look at all possible sets where you take out feature I, when you are computing the Shapley value for feature I, and then you do the difference with I in and I out, and you do this summation, which is of course usually impossible to do. But this is what you should do in theory. Okay? Questions? So of course it's computationally very hard to do, so people usually don't do this, they approximate, but this is how you should do this if you want to do it exactly. So what is the bottom line? We plugged in here the values and we computed them, and we got fairly different values from the decision tree 1 to decision tree 2. And it's worse than that. So here, so this is the values in theory, it has nothing to do with the tool. And here you say that feature 1 has no importance to decision tree 1. Despite everything I said from the beginning, if you compute the values in theory, it says, yes, the most important feature here is feature 3. Either to change or to fix the value of the prediction. This, of course, does not make any sense. Right? So, oh, yes, and of course here, these values are also not very good, but still, since this one is the highest one, you still say, oh, it's more or less okay. These ones are completely nonsense. So the bottom line is that Shapley values can mislead human decision makers, because if it's not a decision tree, if you have a neural network, and if it says the most important feature is feature 3, it could be completely fooled. Because actually we know by looking at the model in this case, the most important feature is certainly feature 1. Okay? And of course, the tool itself is problematic, so we have results showing that, but this is, in theory, there is a problem with the formulation of Sharp. Okay? So, to be clear, the tool itself can approximate misleading values when the theory gives you misleading values. Okay? Very good. So, what did we do after discovering this? What we understood, and this was with the help of a PhD student, yellow up there. So it's the characteristic function based on expected values is extremely problematic. So people in game theory don't use this type of characteristic functions. And so what we did is characteristic functions in game theory usually account when the element is critical for some element. That's when it matters. Everything else should not matter. And so, for example, if you are doing collisions, you care when an element is critical for a collision being winning, and if you take it out, it's not winning anymore. So what we did is we used this idea, and we proposed the characteristic function, which is 1 if the set X is a weak XP, and 0 otherwise. So a nice connection with logic. Okay? So essentially, we have critical elements when if you add the feature to the set, you get a weak XP, and if it's not there, it's not a weak XP. So you're not fixing the prediction. Okay? So actually, the idea is not ours. As far as I can recall, it goes back to the work of Shapley-Shubik in '54, where they used the same idea for voting power. Of course, they didn't have a weak XPs, but it's the same concept. Okay? Yes. And so this is that's the only change. Everything else is the same. We just change the characteristic function. And of course, now we do this, right? So how do we do this? And what we did was as follows. Oh, by the way, all known issues of sharp scores, at least the ones we reported, disappear if you use this characteristic function. We have all the problems with misleading, all of that vanishes. Okay, so, and the punchline I would like to emphasize is that now you have sharp scores based on logic-based explanations. Okay, so I'm running out of time. So Shapley, you can estimate Shapley values using the CGT algorithm. So it's Castro, Gomez, and Tejada. So it's a paper from 2009. It provides you very strong theoretical guarantees of the approximation. That's what we use. but we still are not off of the hook, because how do we compute weak XPs for a neural network, which we can do 30 neurons and you can have a few million, right? So what we did is we test for it, but what we do is we target, where is that? So we sample the model, so for example, we can use training data, and then we use sample-based weak XPs to do this, okay, which we can do in polynomial time. So that's the tool we developed, and we compared SHAP with new SHAP, so our tool is new SHAP, of course. So we use, for comparing rankings, we use rank bias overlap. For some of you, this should be known. Paper from 2010. So essentially, RBO, rank bias overlap measure, if you give it two arrays, it says how similar the two arrays are. And of course, if they are the same, it's 1. As you change, values go down. So here, I think, no changes? Yes. So as we change the arrays, you can see the values. So okay, I cannot go up. Yes, so it's 1, 1, 0, 0, 4, 2, and then if you change a lot the array, you get 0. Okay, and then we tried several things. So we tried a linear regression, decision trees, KNNs, boosted trees, CNNs, different data sets, and then we compared with SHAP, and as you can see, correlation sometimes exists. Most often it does not. Sometimes it exists, but sometimes it does not exist at all. So this means that what you're getting, and to make sure that the comparison was fair, at least as far as we can tell, we use the same sampling that SHAP is using. So the explanations are computed given the sampling that SHAP runs. Okay? So there is no correlation. So essentially there is a problem in theory and in practice regarding SHAP. So that's the bottom line. Okay. Can I continue? You can ask more questions when I'm done. Running time is more or less the same, not a problem. So let me try to wrap up, trying to keep up with the time schedule. So some words of concern. So I started looking at this in 2023. At the time, the SHAP paper had 13,000 citations, which is quite a nice number for many people. Then in 24, it was 28,000 citations. Then last year, September, it was 40,000 citations, but the curve should get you very worried. If it did not, let me show you what I discovered a few days ago. It went up to 51,000 citations, going up the roof. It's completely crazy numbers, right? A tool that not only the theory is flawed, but the tool itself is flawed. And so as I said, theoretical SHAP scores can be mislead, and the results are of poor quality given the sampling that is being done. So, and you could say, come on, nobody uses it. No, there are lots of citations, there are lots of uses, very sensitive uses. So I checked. So blood glucose prediction in diabetes, again, it goes on. So and everybody's using SHAP. So I'm not lying, it's you can check the papers, right? So the bottom line, I believe that there will be massive retraction of papers in a few years. I started saying this 3 years ago, and I'm still saying it. Nothing happened, but I'm still saying it. Maybe in a few years, there will be a huge, massive retraction of tens of thousands of papers because they are using something that is completely flawed. And of course, for those of you that go to the hospital, check if the decisions that you're being given or recommendations are not based on SHAP, because, or at least explanations, right? Because they can be quite wrong. Okay, alternatively, and this I should emphasize, this is from a PhD thesis, 2025. But I need to read it if you guys don't mind. Finally, we know that certain studies have pointed out the limitations of SHAP, and we are in the middle. However, it has been used extensively in the literature due to its demonstrated effectiveness and has contributed to significant discoveries in science, engineering, and business, which were discussed in publications in leading journals such as Science, Nature, Machine Intelligence, Nature Communication, and Management Science. See, just to name a few, the paper by Lundberg has been cited more than 34,000 times. So to this, I think it's a soundness by acclamation. So lots of people are using it. So of course applaud and say, yes, it's good. Well, I disagree, but I could not resist. So by the way, if you guys, anyone is interested, so symbolic XAI, just a few guys. Non-symbolic, as I just showed, at least 50,000 people swear by that. And of course, the difference in momentum is disconcerting. So one of my papers is like, I think now it's 180 citations on showing that SHAP is wrong. And then SHAP is 51,000 citations. So it's not even a fair fight, right? So, and there are worrisome uses of SHAP. So more awareness, of course, would be very important to stop using these misconceptions of non-symbolic XAI. Okay. So what did I do? I started by saying this is more or less what people do in non-symbolic XAI. I gave you a very brief contact with logic-based XAI. And hopefully you saw that the definition of reflective and contested explanation is rigorous. I try to highlight seriously several misconceptions of non-symbolic XAI, rules that are not rules, and approximate something that is misleading. And that interpretability is, of course, a misnomer, so you cannot have that. And of course, I also talked about what we have been doing to replace SHAP, if that is even possible. So what are we interested in? We still think we don't understand the differences, so we are trying to understand the differences. We continue to tackle scalability using, of course, logic-based XAI, distance-restricted explanations, and trying to put in practical use model-agnostic logic-based XAI, which again, it's not many people are looking at this yet. And of course, there is the elephant in the room, not me. The elephant in the room, of course, is I started with LLMs. Where are the LLMs, right? Well, yeah, we are not there yet, but we have some ideas. So if you guys want to discuss it, I will be more than happy offline to discuss with you. Okay. And that's it. So thank you.